All right, now we get into finally some more fun stuff with the chemistry curriculum, and I really do think that a lot of folks enjoy balancing equations. So that's what we're going to be on about now. My title here says equations and stoichiometry, but really, I think what we're going to do is we're going to push stoichiometry off to another lecture and keep this one just the balancing of equations. So, if you look at a word problem like this, and I wanted to start out with a word problem on purpose because it shows you what you already do know from this course. So thinking about, let's see, what do we have here? Copper 2 nitrate, and it tells me nitrate is going to be one of my polyatomics. So NO3 with a 1 minus charge on it, and let's see, copper 2. So that tells me that this guy has a 2 plus charge because it's one of our transition metals, and we have to specify the oxidation state there. Okay, well, 2 plus and 1 minus, so it's going to take 2 of these nitrates with every copper. So it's going to be Cu, parentheses, NO3, close parentheses with a sub 2 on that. And then similarly, sodium hydroxide, NaOH, copper 2 hydroxide, Cu, parentheses, OH, close parentheses with a 2, and then sodium nitrate, NaNO3. All right, so that part you already know how to do from our ionic formulas stuff back on exam 1. So let's take this now. We'll turn it into a chemical equation, right? So we'll write out each of those things this way. So there's our copper nitrate. Don't worry about this AQ. I'm going to talk about those in a minute. Here is our sodium hydroxide. At least for me, you can put parentheses around the OH if you want to sometimes. That makes it make a lot more sense to folks. So it is perfectly fine. You don't have to have them since there's a single OH polyatomic on this. It's not required to put a parentheses, but it's certainly allowed if you would like to do it. There's our copper hydroxide and our sodium nitrate. Okay. So what we have to do is we have to think about, this is really about accounting, okay? So if we look at this, copper nitrate, right, what are we looking at? So it's like this. We've got this copper atom, and then we've got 2 nitrate groups around that central copper. And then similarly here, we've got our sodium, which I've done purple here. I'm color coding these so that I can track them on the other side. And then this is going to be our oxygen and hydrogen, so that's our OH. The other side, we've got this copper, right? And we got 2 of these. This is like that OH right there. There's an OH. So we got 2 of those on it. And then we've got a sodium nitrate there. Okay, so the essence of this is the law of conservation of atoms, right? So absent a nuclear reaction, which we're going to get to much later in the semester, not yet. But absent some sort of nuclear reaction, we have nuclear fission or fusion or something like that, or other capture processes or stuff, you can't change elements. So, however many copper atoms you start with, or moles of copper to be more proper, but I think for this initial approach of balancing, let's just talk in terms of single formula units, and we'll call this 1 copper atom. So we've got a copper atom here. We have to have the exact same number of copper atoms on this side when we end up, because we're not allowed to create or destroy copper atoms. Similarly, we have to count up all of our nitrate. All of our nitrogens, I should say. We'll do this on the basis of single atoms because later on our polyatomics can change. So don't just say nitrates here. We'll talk about the nitrogens, the green ones I have here, and then the oxygens that we have. So we'll total them up and try to balance them on the other side. So let's look at this and see if they're balanced. Let's see. Right now we've got 1 copper on this side, and we've got 1 copper on this side. So coppers are good. That sounds great. What about our nitrogens? So this is a green one here. Well, we got 2 nitrogens on the left. Uh-oh, wait. we only have one nitrogen accounted for. Where'd the other nitrogen go? We got to figure that out. Let's look at some more of them. Let's look at this sodium because it's easier. My purple sodium here, looking on this. Okay, sodiums are fine. So we decided copper is fine, sodium is fine, but the nitrogens are not. About hydrogens, that red, there's one on this side, but there are two over here. That might not be good either. And then let's look at all these oxygens. We got 1, 2, 3, 4, 5, 6. Now, you could just multiply these and get 6 here, but don't forget there's 6 on the copper nitrate. There's also one here on the sodium hydroxide. So we need to count all the oxygen atoms, these 6 plus this 1. That's 7. And over here, we've got 3 here and 2. That 2 applies there. So we only got 5. Okay, well then, that's not balanced because we're not accounting for everything. It's not equal on both sides. What's happened? Well, now, I could look at this and I could say, you know what? That looks almost like, let's see, a nitrogen. We're missing some oxygens too. Need another nitrate there. Now, the nitrate can't just be hanging out there by itself. It would have to have a sodium to go with it. So I'm going to give it some more sodium by balancing that over here. And when you do that, you recount and you see that actually now we can account for everything. And we have the same number of each of these elements on the left side as we do on the right side. Now, we need to indicate that. We won't always draw this pictorially. We need to indicate it with our chemical equation, and we do that with what are called coefficients. So coefficients are going to go out in front, right? So let's see, we didn't change this, so we still have one of these, but now we need 2 sodium hydroxide units. We still have 1 copper hydroxide, but we need 2 sodium nitrate units. And so we'll indicate that using coefficients in front of the chemical species. Please do not try to insert coefficients in the middle of a chemical formula, not allowed. And please do not change subscripts as you're doing this, not allowed. Once you've built your copper nitrate or your sodium hydroxide, once you've built that, leave it alone. Only change the big numbers out front, which means how many of that whole unit. So this big red 2 here means there are 2, 1, 2 sodium hydroxides. This 1 means there's only 1 copper hydroxide. 2, 1, 2 sodium nitrates. That's how this little game is going to work. Like always in chemistry, there's gonna be some terminology. So this is another system where I'm probably gonna run into terminology without thinking. I'm gonna say things without thinking about it. And y'all have got to stop me and get me to explain terms that I use that are not familiar to you. Make sure we're talking about the same stuff. Make sure we're in the same conversation. But the ones that I thought about to your book has a lot of these that I want to point out. So an equation is going to have 2 sides to it, okay? We talk about the reactant side as the left side of equation. So these species over here are going to react together to generate these species over here, which we're going to call product side. So your reactants react to produce products. Okay, we'll call each one of these, in this case CH4, is a reactant. O2 is also a reactant. CO2 is a product, H2O is a product. You get the idea there, right? And nothing magical about 2. You could have 17 if you wanted to. Be kind of hard to balance though. Pointed out on the last slide that the number here is a coefficient. I'm going to add, let's see here. I think that you need coefficients in the case of ones also. I like for you to write these ones, or this 2 in that case. I like for you to write those ones to keep it from being confusing. You don't really have to do it, but I think it makes your life easier if you get in the habit of showing the ones. We call it a coefficient. It does apply to the entire thing, so you'll see that change back to my laser pointer here. You'll see that 2 means there's 2 O2s. So this red here, that's an oxygen molecule bonded together. So there's one oxygen molecule, there's another whole oxygen molecule. Okay? So the big 2 out front is a coefficient, and it means 2 of the whole molecules. Same thing for the waters. Okay. These show up sometimes and not always. And when they come into play, when we actually use them in chemistry is when they're going to be important in the reaction. But to be honest, you're in Gen Chem 1, so they're going to show up sometimes probably just to confuse you. The textbooks, some textbooks use them all the time. Some use them some of the time. I tend to use them only when they're going to be needed for what I'm doing chemistry-wise. What they mean are basically so I'm going to use the term phases here. Later in Gen Chem 2, we talk about the difference between states and phases. But for right now, just think of phases as being a broader term. So you've got S for solid, L for liquid, G for gas. That makes sense probably as the 3 primary states that you've thought of before. But then here's a new one. Aqueous means dissolved in water. Okay, not any solvent. AQ is specifically in water. And then sometimes I'll put this in XLL, which stands for crystalline. That might matter, especially since you've got an old geologist teaching this, and I tend to think of a lot of things in terms of crystal chemistry. Okay, so how does it work? So a lot of times you'll be able to kind of just look at it and make it work in your head for some of the easier ones, right? Now looking at this one, what do I see? I see that I've got 2 oxygens and 2 hydrogens on the left. Now I'm starting with ones here, right? Comes with ones, just not written. But when I do that, look, I don't have enough oxygens over here, right? So I need to say that needs to be 2 water molecules. Now if I double everything here, right, instead of 2 hydrogens, I'll have 4, and I'll have 2 oxygens, which fixes the oxygens. But oh, look here. So then if I just also make that a 2, so I've got 2, 1, 2, and it is nice and balanced. So that would make it a balanced chemical equation. Now, obviously, they're not all going to be this easy. I'm going to show you a step-by-step method in a minute. But for the ones that are really easy, you don't have to go the whole step-by-step method. You can just keep it simple and just balance it by inspection. All right, let's try it again here. Let me see. What do I see? 2 hydrogens. That's good. 1 oxygen on each side. Okay, 2 hydrogens on that. Yep. Oh, wait. Sodiums. Oh, but look, sodium is by itself. That's a nice situation because that means that even though I've got ones in front of all of these, right, then I can just say, look, though, if I just had 2, so 2, 1, 1, 1 would balance this guy out because it would double this. Let's go purple there. It would make it an extra one there, and we'd be all nice and balanced, right? So far, so good. Now, please do be careful of these traps, right? So you start trying to balance this and you get all crazy, but you could have started out this one by saying, let's see, what we count here: 1, 2 hydrogens, 1, 2. I Got a green carbon, got a carbon, got 1, 2, 3 oxygens, and oh, you know what? Look here. 1, 1, 1. This one's already balanced off the bat. Wasn't difficult at all, right? But now you know they're not always going to be this easy, right? Okay, well, let's take a look at this guy. What do we have here? This is where I'm going to show you my step-by-step method, okay? So I've got, what do I have involved here? I've got a bunch of different elements. We're going to have to do some work to make this work. So what I like to do is I like to list my elements right down the middle here, directly under the yield sign. There's nothing magical about the way I'm doing this. It's just all this is just bookkeeping. Another habit that I have is to often, not always, but often, try to do oxygen and or hydrogen last, because sometimes they just accidentally balance themselves, or more importantly, sometimes they are by themselves. See how that oxygen is by itself? That means we should save it for last, because it can kind of clean up whatever mess we make, because we can get more or less oxygens just by itself. Okay? So I'm going to list everything. I've got carbons involved. I've got hydrogens involved. And I've got oxygens. That's the only 3 elements involved in this entire reaction. All right, so then I'm going to assume that we have ones starting out with everything. Then I'm going to total my elements so far. Let's see, 1 times 4. I got 4 carbons on this side, and I've only got 1 carbon on this side. Please don't make the mistake of this. Remember that the 2 only goes with the oxygen here, not with the carbon. There's no parentheses around the CO, right? So the 2 only applies to the oxygen. Okay. Let's look at the left side. Hydrogens, we've got 10 of those. On the right, I've only got 2. So that's not balanced either. Oxygens, I've got 2 on the left. Now, this is going to happen a lot, so make sure you look in all the places. I've got 2 oxygens here in my carbon dioxide. But I also have 1 oxygen in the water molecule. So 2 plus 1, I've got a total of 3 oxygen molecules. Okay, so my trick is to save oxygen and hydrogen for last, and in this case, oxygen by itself, oxygen for the very, very last. I like to do metals first. I don't have any metals in this case. Then my nonmetals, we're going to call carbon a nonmetal here, and then that oxygen and hydrogen last. So that's going to be my order of attack. Okay, so let's see. Looking at my carbons. So I've got 4 carbons on the left, 1 carbon on the right. So what I'm going to do is I'm going to say, well, I'm going to need 4 carbons. The way I get that is by 4 carbon dioxide molecules. So I'm going to put a 4. All right, this is going to be something you probably are not going to want to do because it's more writing, but I promise you it saves you mistakes later on. I made 1 change up top. I marked out all of my elements, and I recalculate all of them, including the hydrogen, which is not going to change. The reason for that is if you try to just change some of them, you will forget some, and you will make mistakes. So if you mark them all out and recalculate the entire side, so I have 4 carbons. I have hydrogens. Let's see, nothing changed here. 1 times 2, I've got 2 hydrogens. Now oxygens, I got 4 times 2, so 8 oxygens there, plus 1 times 1, so plus 1, so now I have 9 oxygens. Okay, so far so good. I got my carbons. Let's see, we were going to save oxygens for last, so let's go to hydrogens next. Let's see. I've got 10 on the left. I only have 2 on the right, so I need some more. Let's do another color here. Let's do green. Let's see if it shows up. So I'm going to change that. It's a good place to get hydrogens. So I need 10. So let's try a 5. All right. Let's see what happens if I do that. So I said I wanted to change everything. I'm going to want to retally everything, right? So even though my carbons didn't change, I mark it out anyway. 4 times 1, so 4 carbons. Hydrogens. 5 times 2, 10 hydrogens. Okay. Then let's see now oxygens. I got 4 times 2, that is 8. Okay. Plus 5 times 1, that's another 5. 8 plus 5 is 13. Okay. So now we've got carbons, hydrogens, and everything but oxygen is fixed. So let's see. To get, now oxygen is by itself, and that's good. Oh, but wait. If I tried to get, let's see, I need 13. So if I tried 6 here, it would give me 12 oxygens. Not enough. Well, one more, 7 here would give me 14 oxygens. There's no way to get an odd number. Okay, I'm going to tell you 2 different answers here. Both of them are correct. In upper level chemistries, maybe. Definitely in geology, a lot. We would just use a fraction here, right? So this, we would just use 13 over 2 and be done. But most of the folks in chemistry don't like that, so I'm going to show you the way to do this without using fractions. If you balance this with a 13 over 2, I am perfectly fine with that. It works, no problem whatsoever. And the ratios all work out exactly the same, so it's all cool. But most people don't like using fractions. So when you encounter this situation where you've got an odd and things are only coming in evens, what the trick is to go through and double everything. So I'm going to change this to a 2. Change this to a 2. I said everything, but don't mess with the subscripts. They don't change. The 4 becomes an 8. 5 becomes a 10. Now you can recalculate these, but since you double everything, everything just doubles, right? So that's 8, 20, and 26. Okay, and this is 8, 20, and now 4. Okay, so see, my carbons and hydrogens are still fine. They're still fixed. Everything's still fine except for the oxygens, but the trick is that now I need 26, which is an even number, right? So I can just change this to a 13. Recalculate this side. Let's see, I still got 2 times 4 is 8 carbons. 2 times 10 is 20 hydrogens. And 13 times 2 is 26 oxygens. Okay, so according to chemistry, our equations are 2. Our coefficients are 2, 13, 8, and 10. If you balance this with 1, 13 over 2, 4, and 5, that is also a correct answer. Okay, so now you're good at it, so you can just do this, right? Now, to be honest, that equation looks intimidating, but if you'll use my step-by-step method here, this one's not so bad either. So it looks terrible. What we got is the mineral formula for perophyllite. Perophyllite and water. That's a weathering equation. Yields. I've used the term yields here. That's the same thing as the reaction arrow. And then you've got kaolinite. Georgia is famous for its kaolinite. This is how it forms. And then you've got, this is called silicic acid. We'll talk later about the acidy part of acid, which is the H's hanging off the front. So if you've got these chemical formulas, and I would not expect you to be able to create these chemical formulas, by the way, so please don't stress about that. But if you've got these, how do you balance it? Well, I'm going to claim that by following that simple method that I gave you earlier, this is all going to it's all going to work out more easily than it looks like it will. Okay, so what's my first step? My first step is to list the elements involved. Well, I've got aluminums, I've got silicons, oxygens, and hydrogens. Now, even though these are fairly complicated, right, it's still only those 4 elements involved. Okay, now I'm not sure why I did the tallies up here and then did them again, but okay. So remember, it comes with ones, right, in front of all these. So now we can start to, I made a step-by-step list here. We listed the elements, we did that, okay, and then we're gonna put those coefficients in, okay, and then I want to count how many of each of those we have to start with, right? So we have 2 aluminums on the left, right here, right? We've got 4 silicons. Oh, I did the 2 aluminums on the right first, okay. Then I'm going to do silicons. So I've got 4 here, right? Okay, on the right. Now be careful here. You've got 2 silicons here in the kaolinite, but you also have 1 in the silicic acid, so that's a total of 3. All right, now oxygens. Wow, there's a lot of oxygens to count, right? So 10 here plus those 2 in the hydroxides, right? So 12 in the peroxide plus 1 in the water, right? 13. On the right, let's see, I've got 5 plus 4 in the hydroxide, so 5, 9, plus another 4 here. Well, that's 13 also. That's not too bad. Okay, good. Hydrogens, let's see, 2. Oh, there's another 2, 4. 4 on the left. And on the right, I've got those 4 there. Oh, wait, and those 4, so 8. Okay. All right, so that's where we are right now. We totaled up everything. All right, now my step 3 is I'm going to increase coefficients. Only the coefficients, these big capital ones, capital number. But okay, these big ones here, right? I'm going to increase those to try to balance things out, right? So what I'm doing is I'm saying aluminums are fine, silicons are my next target, and I can get a silicon right here. I could have gotten it here also, but I evaluated and decided this was a better target because I can get 1 more silicon there. So I'm going to change that coefficient to a 2 instead of a 1, right? I'm going to mark everything out and recalculate, right? Now I have still 2 aluminums, that didn't change. 4 silicons now because I've got 2 here, plus I've got 2 of these silicic acids, each with 1. So 2 here, 1 times 2 here, 2, plus 2 times 1 here, so another 2, so 4 total. Be careful in the oxygens, right? So this is 9 still, but now I have 2 of these out here, so 9 plus 8 for 17. 12 hydrogens, 4 plus 8, okay? All right, so let's evaluate again. Aluminums and silicons look good. Uh-oh, my oxygens now. Oxygens were okay, and now they're not. Okay, well, fine. We're going to get some more oxygens. Now, we have 2 choices. We could get more oxygens in here, but here, look what's going to happen if we do that. We're going to mess up all this aluminum to silicon ratio. I think it might be easier to go for oxygens here. Now, sometimes you try something like that and it doesn't work out and you end up having to back up. Don't be afraid to back up sometimes on this, okay? But I'm going to try marking that out and getting some more oxygens. Let's see what that did. So I've got 10 plus 2, right? That's 12 there, plus 5 times 1. Hey, yeah, that did work. Let's do everything here. So we got 2 silicons still. 2 aluminums and 4 silicons. And now we're at 17 oxygens. All right, let's evaluate those hydrogens. What we have 2 in the peroxide plus 10. So that's 12. Oh, look. One of the reasons you leave oxygen and hydrogen for late in the process is because sometimes they just randomly fix themselves at the end. It's not really random. It's deterministic because they come in certain chemical packages, but okay. All right, so I think that's the basic process, and we're going to spend time practicing these balancing equations. It does look simple, and it is if you take it step by step, although I admit that there are some really, really hard equations out there to balance. So when you want extra practice on these, there are some really good websites out there that give you practice. Just Google practice balancing chemical equation. And there are lots of them that'll just throw up random equations for you to play with and balance, and it'll check you and stuff like that. If I have any of you that are really, really in love with the math, if you want to do this in an entirely mathematical way, there is a way to do this using systems of equations. I'm not going to put that in the video, but if any of you want to know the pure math way to do this, ask me in class and we can walk through that if you really want to do it. I don't use it very much except for seriously hard ones. To be honest, a lot of times you go to Google's for those, but you can do just about any equation without resorting to Googling or to using the systems of equation approach. But some folks that really, really like maths will want to use the system of equations approach. Okay, and so where that leaves us is now I've moved stoichiometry off, and we're going to make it a lecture by itself now. There's a reason for that. Looking at Chem 2, looking at what students struggle with, sometimes we're gonna put stoichiometry all by itself in a lecture and try to really, really focus on it. I'll put the exclamation marks here because I actually do love stoichiometry. I think it's one of the most powerful things in Gen Chem, and I do think it is the absolute most important concept in all of General Chemistry 1. Possibly in all of General Chemistry, period, but definitely in this first course. So reread any parts of Chapter 4 that you need for this, that you've not totally internalized, but especially 4.2. 4.2 is the straight up stoichiometry part, and then 4.3 and 4.4 have to do with yields and limiting reactant, and those are going to be super duper important as well. Okay, see you in class.